Rolle's theorem, lecture 2. Statement of Rolle's theorem. If a function f is continuous on the closed interval ab and differentiable on the open interval ab such that fa equal to b, then f dash c equal to 0 for some c with a is less than or equal to c is less than or equal to b. Question number 1. Discuss the applicability of Rolle's theorem for function fx equal to x squared plus 1 when 0 is less than or equal to x is less than or equal to 1 and 3 minus x when 1 is less than or equal to x is less than or equal to 2. So here two things are important. First, we will check whether function is continuous, and then we will check whether function is differentiable. If both the conditions are satisfied, then we will proceed. So let's see first condition. So at x equal to 1, we are going to check whether function is continuous or not. So LHL limit h tends to 0 and we write f1 minus h. So this will give 1 minus h square plus 1 limit h tends to 0. So this will give 2 and we try RHL. So limit h tends to 0, 1 plus h in function. So function 1 plus h will give 3 minus 1 plus h. So this will give 2. So LHL equal to RHL. Hence we say that function is continuous at x equal to 1. Now we have to check differentiability. So left hand limit L f dash 1. So for this purpose we write limit h tends to 0 and definition of derivative 1 minus h minus f1 divided by h. So this will become limit h tends to 0, 1 minus h square minus plus 1 minus f1 is 2 divided by h. So on simplification, we will get 2. Now, the right hand derivative r f dash 1 we evaluate. So limit h tends to 0, 1 plus h minus f1 divided by h. So this will become limit h tends to 0 and 3 minus 1 plus h and then plus minus 2 divided by f1 will become here minus 2. So here if we put, we are taking this one for right hand limit. So we put x equal to 1. So this will become 2. So that is why f1 equal to 2 whole divided by h. So this time we will get minus 1. Since left hand derivative is not equal to right hand derivative, so we can say function is not differentiable. Since second condition of Rolle's theorem is not satisfied, so we can say Rolle's theorem will not hold for this function. Now, question number 2. Discuss the applicability of Rolle's theorem for fx equal to tan x in 0 to pi range. 0 is less than or equal to x is less than or equal to pi. So here fx equal to tan x. Now we put fx equal to 0 to get the value of x. So tan x equal to 0, which gives x equal to 0 and pi. Also, we put the values f0 will be 0 and f pi will be 0. So we can say fa equal to fb condition, that is f0 equal to f pi is satisfied. Now, we have to check whether function is continuous or not. So we know from the graph of tan at pi by 2, it becomes infinite. The graph is like this. So function is discontinuous at pi by 2. So this is one of the condition for Rolle's theorem to be satisfied. So since function is discontinuous, so Rolle's theorem is not applicable for this question also. Next question is, verify Rolle's theorem for function fx equal to x cube minus 6x squared plus 11x minus 2. So the two conditions, continuous, the function is continuous, and it is differentiable because it is a rational integral function. So both conditions are satisfied. So now we have to find out the value of x. So fx equal to, we are given x cubed minus 6x squared plus 11x minus 6. Now we factorize it. So we take common x cubed. Let's write it here. Fx equal to x squared common. Then here we have to write it like this: x cubed minus x squared minus 5x, and then plus 11x minus 6. Now one more term is needed, so that we will make here. For this we will break it. So x square common, x minus 1 minus 5x common. Here also we have to make x minus 1. So for that purpose, this will become 6x. Now 5x will be left. So here we write it as 6x minus 1. Now purpose is search. So we can write it x minus 1 times x squared minus 5x plus 6. Now we further factorize. So it will become x minus 1, x minus 2, x minus 3. So if we put fx equal to 0, so we will get 3 values. So x for fx to be 0, x equal to 1, 2, 3. Now we have to check whether f1 equal to f2 equal to f3. So let's see. If we put 1 here, so this is 1 cube minus 6 plus 11 minus 6. That will be 0. If we put 2 here, so 2 cube is 8 minus 6 into 4 plus 11 into 2 minus 6. This will also get 0. Similarly, if we put 3 here, so 3 power 3, that 27 minus 6 into 3 power 2, 9. 9 6 54 plus 11 into 3 minus 6. This will also get 0. So we can say f1 equal to f2 equal to f3. All three are equal to 0. So the conditions of Rolle's theorem are satisfied. So let's find out the value of c. So let's differentiate it. F dash x equal to 3x squared minus 12x plus 11. We put it equal to 0. So f dash x equal to 0. We can apply quadratic formula. So x will be minus b, that is 12 plus minus 12 squared 144 minus 4ac. So 4 into 3 into 11 divided by 2 into 3. So this will give 2 plus minus 1 by root. Now we have to check the value of x in different intervals. So for that purpose, we write 1 is less than, we take 2 minus 1 upon root 3 is less than 2. So this is one value of c which lies in the given interval. And similarly, if we take 1 and 3, because we have these values, so interval will be 1 2, 1 3, 2 3, etc. So now we are going to take interval 1 3. So second value 1 is less than 2 plus 1 upon root 3 is less than 3. So this is another value of c, hence Rolle's theorem is verified. Question number 4. Verify Rolle's theorem for fx equal to x squared in interval minus 1 and 1. So this is a rational integral function. So definitely it will be differentiable and continuous. Now we check the conditions. F minus 1 equal to 1. F1 is 1. Hence we say that F minus 1 equal to F1. So this is one of the conditions for Rolle's theorem to be satisfied. Now let's find out its derivative. F dash x, that will be 2x. We put it equal to 0. So 2x equal to 0. So we get x equal to 0. So we can say the value of x, that is c, or we write it c equal to 0. So value of c lies in the interval -1 is less than 0 is less than or equal to 1. This is value of c. So we say that Rolle's theorem is verified. Thank you for watching.